Preparation of ether. First, by dehydration of alcohol. The alcohol undergoes dehydration in the presence of protic acid, that is sulfuric acid or phosphoric acid, like this. Here, the formation of the reaction product alkene or ether depends on the reaction condition. See, here the alcohol treatment with sulfuric acid at 443 kelvin mean you will get alkene. That's mean ethene. Already we were seeing the mechanism also. Then the second, look at the second is in 413 Kelvin. The same acid, but temperatures differ. So the temperature differs means you will be getting ether. This is diethyl ether. Now look at this mechanism, how the formation of ether here. This is also the three-step mechanism. The first step, alcohol react with acid to form a protonated alcohol. This lone pair of electron to stabilize the positive charge and to form oxonium ion or protonated alcohol. So this protonated alcohol, again treatment with 1 mole of alcohol to form again like this. See the lone pair of electron, this oxygen to stabilize the and this positive charge is stabilized by this bond and H2O molecule goes out to form like this. So here the positive charge, O having the positive charge because one lone pair of electrons goes away. Then this compound again stabilized by the positive charge by itself in the hydrogen atom to form ether, that is diethyl ether or ethoxyethane. So this is the formations of ether from the dehydration of alcohol. This acidic dehydration of alcohols to give the alkene is also associated with the substitution reaction to give an ether. This means the method is suitable for the preparation of ether having the primary alkyl groups only. So this is the primary alkyl groups only. The alkyl group should be unhindered and the temperature be kept low. Otherwise, the reaction favors the formation of alkene. So here the temperature is what? 413. But here the 443 means it gives alkene. So the reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you learn in higher classes. However, the dehydration of secondary and tertiary alcohol to give the corresponding ethers is unsuccessful as elimination competes over substitution, and as a consequence alkenes are easily formed. Then Williamson synthesis. Preparation of ether from Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and the unsymmetrical ether. So in this method an alkyl halide is allowed to react with the sodium alkoxide. So the alkyl halide react with the sodium alkoxide to form ethers and the sodium halides. Look at this. The ethers containing the substituted alkyl group, that is the secondary or the tertiary, may also be prepared in this method. The reaction involves SN2 attack of an alkoxide and the primary alkyl halide. So SN2 attack here. Then look at this, the reaction. The better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution. So if a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, look at this reaction. The sodium. First, look at this reaction. The tertiary compound, the NaO plus. See, this is the alkoxy group and the sodium. And look at this CH3Br. First, the negative charge of the oxygen atom to attack this, and this bond is shifted here. So the NaBr is formed. This means NaBr is formed, then the ether is formed. Here the next in, suppose if you use like alkyl halides, there is tertiary alkyl halide. that is sodium methoxide, react with the sodium methoxide to form what is the product mean? The NaBrS goes out. Then usually you can see the NaBrS goes out, but not like that. Is here the formation of what? Alkene, not as ether is formed. Already I said there is the secondary and tertiary alkyl elimination competes over the substitution. So if tertiary alkyl halide is used, alkene is the only reaction product, no ether is formed. This is a formation of 2-methyl propene. It is because of alkoxide are not only the nucleophiles but strong bases as well. So they react with alkyl halides leading to elimination reaction. And the phenols are also converted into ether by this method. And this phenol used as a phenoxide moiety. Look at this, the phenol treatment with base to form sodium phenoxide. Then the sodium phenoxide again treatment with alkyl halide, this methyl halide to form anisole. Then physical properties. The physical properties of ethers usually ethene, that means alkene, ethers, alcohol has the carbon oxygen bond. The carbon oxygen bond in ether, they are polar, and thus the ethers have net dipole moment. So the weak polarity of ether do not appreciably affect their boiling point, which are comparable to those of the alkanes of comparable molecular mass, but are much lower than the boiling point of alcohol. So look at the N-pentane, ethoxyethane and butane 1R, alcohol, ether and alkane. The boiling points are 309.1 Kelvin for N-pentane, ethoxyethane 307.6 Kelvin, and ethanol is 390 Kelvin. See the large difference of the boiling points of alcohol and ethers due to the presence of the hydrogen bond in alcohol. Look at this, the hydrogen bond. Thus the miscibility of ether with water resemble those of alcohol, the same molecular mass. Both ethoxyethane and the ethoxyethane and the butane 1 all are miscible to almost the same extent. That is 7.59 gram per 100 ml of water. That is 7.5 and 9 gram per 100 ml of water. So the respective, while the pentane is essentially immiscible with water. Why this happens means this is due to the fact that just like the alcohol, oxygens of ether can also forms a hydrogen bond with water molecule. So look at this. Then cleavage of CO bond in ether, that is chemical reaction. Cleavage of CO bond. Carbon oxygen bond. Here ether are the least reactive function. The cleavage of the CO bond in ether takes place under drastic condition with excess of the hydrogen halides. See ROR ether react with the hydrogen halide to form RX and ROH. So RX and ROH like this. Alkyl halide like this. Then the ROH react with HX, that is excess of hydrogen halide. So excess of hydrogen halide forms RX and water molecule. Like this. So the alkyl aryl ethers are cleaved by at the alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yields phenol and the alkyl halides usually. The phenoxide react with the alkyl hydrogen halide to form phenol OH and RX, alkyl halide. So ethers with the two different alkyl groups also cleaved in the same manner. Look at this different alkyl group CH3 and C2H5 react with the hydrogen bromide. So what happens means they form CH3Br and the remaining is C2H5. CH3Br just like this, and the remaining is what? Alcohol, ethanol, C2H5OH is formed. That is alkyl halide and alcohol is formed when the different that is the unsymmetrical ether react with the hydrogen halide to form alkyl halide and alcohol. So the order of the reactivity of hydrogen halide usually Hi is greater than HBr is greater than HCl. So the cleavage of the ethers takes place in the concentrated hydrogen iodide or hydrogen bromide at high temperature. Look at the three-step mechanism. The reaction of an ether with the concentrated hydrogen iodide starts with protonation of ether molecule. Look at this protonation of the ether. This is the CH3OC2H5, the lone pair of electron in the oxygen to abstract the hydrogen, and the iodide is the iodine atom is that is goes to iodide ion. This is the protonated ether is formed. In step 2, the reaction takes place with the hydrogen bromide or the hydrogen iodide because of the reagents are sufficiently acidic. So step 2, in this reaction iodide is a good nucleophile. So it attacks the least substitute carbon atom, carbon of the oxonium ion. This is the oxonium ion formed in the step 1. Look this. This is the oxonium ion. And displace the alcohol molecule by SN2 mechanism. Look at this. There is no intermediate transition state. This is the cleavage of the mixed ether with the two different alkyl groups. Then the alkyl iodide, thus the cleavage of mixed with two different alkyl groups, the alcohol and the alkyl iodide formed depend on the nature of alkyl groups. When primary or secondary alkyl groups are present, it is lower alkyl group that forms alkyl iodide. That is the SN2 mechanism. See, look at here, the I minus shifted here like this. Then the positive charges stabilizes. Usually this is the transition state. Then they form like this. The positive charges stabilize like this. CH3I and C2H5OH, alcohol and alkyl iodide is formed. When HA is excess and the reaction is carried out the high temperature, ethanol reacts with another molecule of hydrogen iodide and it's converted to ethyl iodide. Look at this step 3, excess of hydrogen iodide, the ethanol, excess of hydrogen iodide to form the protonated alcohol. This protonated alcohol again stabilized. So the I minus attack like this, then this is stabilizes. So alkyl iodide, that is ethyl iodide and water molecule. However, when the alkyl group is a tertiary group, the halides formed in the tertiary halides. The alkyl group is a tertiary group in ether to form tertiary halides. This is the tertiary halide. It is because of the step 2 reaction. Look at this. The departure of the leaving group, that HCO3, departure of the leaving group, the alcohol, creates a more stable carbocation then and the reaction is, follows SN1 mechanism. Look at this. This follows SN1 mechanism. First step is a slow step, formation of carbocation here. The carbocation again stabilized by the iodide ion. This iodide ion stabilized by then formation of tertiary alkyl halide. Suppose the compound is anisole. That means the methyl phenyl oxonium ion. This is the methyl phenyl oxonium ion is formed by protonation of ether. The bond between the OCH3 is weak than the bond between the OC6H5, because the carbon of the phenyl group is sp2 hybridized carbon atom, and the partial double bond character, therefore the attack of iodide ion breaks to OCH3 bond to form CH3I, that is iodide. Phenols do not react with to give halides because of the sp2 hybridized carbon atom. A phenol cannot undergo nucleophilic substitution reaction, okay, needed to for conversion to halide. Then electrophilic substitution reaction. The electrophilic substitution reaction, the alkoxy group, that is the OR group, ortho-para directing and activates the aromatic ring towards the electrophilic substitution reaction the same way as in phenol. See, look at this, the mechanism, the resonance structure. The lone pair of electron is shifted here, then this bond is shifted here. So it forms a double bond and positive charge is created here. Then this negative charge is shifted here so that it will comes here. Again the negative charge is formed like this. Then negative charge shifted here, then this will shifted here. So the negative charge formed like this, again shifted like this, then to stabilize the positive charge to form like this. So in halogenation, the halogenation, ethers undergo usual halogenation in the benzene ring. In anisole, look at this, anisole undergoes a bromination with acetic acid, bromine acetic acid or ethanoic acid. Even the absence of iron 3 bromide catalyst, it is due to the activation of benzene ring by the methoxy group. Para isomer is obtained by the 90% of the yield. Look at this, this is the anisole react with bromine acetic acid to form para bromo anisole. This is a major product, and ortho-bromo anisole is a minor product. There is a 90% you will get the yield. Then nitration, this is nitration. Nitration of anisole react with this concentrated sulfuric acid and concentrated nitric acid. You will get ortho nitroanisole and the para nitroanisole. The para nitroanisole is the major product, or you can get you can write 2 nitroanisole or 4 nitroanisole. The 4 nitroanisole is the major product. Then the Friedel-Crafts reaction. The Friedel-Crafts reaction, that is the alkyl and acyl groups introduced at the ortho and the para position by the reaction with alkyl halide and the acyl halide in the presence of anhydrous aluminum chloride. That is the Lewis acid catalyst, like a catalyst in the carbon disulfide. Look at this, the methyl chloride, anisole react with the methyl chloride to form 2-methoxytoluene and 4-methoxytoluene. The 4-methoxytoluene is a major product. Look at this, acetyl chloride or ethanoyl chloride. Anisole react with acetyl chloride in the presence of anhydrous aluminum chloride to form 2-methoxyacetophenone and 4-methoxyacetophenone. The 4-methoxyacetophenone is a major product. This is the Friedel-Crafts reaction.